I'm going to present a paper by Professor Drusvyatskiy, Professor Pataki, and Professor Wolkowicz here. The title is Coordinate Shadows of Semidefinite and Euclidean Distance Matrices. So this is a wonderful paper explaining some phenomena that we observed in the literature about a feature reduction algorithm for solving this positive semi-definite completion problem and Euclidean distance matrices. So it's theoretical, but it gives a good, very well explanation of what is happening in the literature. So we're going to start with the first. We're going to start with a linear image of closed convex cones. So for given closed convex cones, we look at its linear image, and we investigate if the linear image remains closed. So assume that we are given a linear mapping A, and C is a closed convex cone. A central question in convex analysis is that is the linear image A, C closed? So you take any elements from the closed convex cone C and compute A applied to that element, and altogether this is itself a closed convex cone. But even C is closed, the linear image AC may not be closed. So this is a very interesting question in convex analysis, and this question is related to several different other problems. For example, the preservation of lower semi-continuity. If you have a lower semi-continuous function f, for example, and you may consider the composition of A and F, and you ask yourself if A and F remains lower semi-continuous, and this question can be related to the problem here by looking at epigraph. Actually, a whole chapter in the classical textbook by Rockefeller, Convex Analysis, is devoted to this problem here. There are also other applications, uniform duality in conic linear systems, in this paper too by Dufin, and the existence of solutions to extreme problems. So I'm not an expert in those problems, but just give you an idea how this problem are why this problem become interesting in the literature. There is a more recent paper by Pataki talking about the relation between the nice cones and the linear image. So let me just give two concrete examples of linear images of closed convex cone. So let's define linear mapping from the set of 2 by 2 positive semi-definite matrices to R2 by mapping the diagonal elements X and Z of a PSD matrix big X to R2 XZ arranged in this way. So it should be clear that the image set is precisely R2. Oh, sorry, it's R2 plus here. I'm sorry, there's plus missing here. Because you can take any positive non-negative elements for X and Z, and simply set Y equals 0, and this is positive semi-definite. Now this set is clearly closed in this case. The linear image is closed. Just to see that image is closed, you simply take a sequence in the image set, and the sequence has this sequence has a limit, and we have to show that the limit remains in this set, and this is clearly the case here. So the image set is closed. As a counterexample, the image set of this linear mapping here is not closed. So instead of mapping the diagonal elements X and Z, we instead map the first row X and the off-diagonal entry Y. Now the image of the PSD cone under this linear mapping is union of orange 0 and positive in the first entry and real numbers in the second entry. So in the picture, it looks as follows. It's everything here, but except this line, but it still contains this zero here. Now this set is clearly not closed. To show that this is not closed, is simply take another sequence here, which converge to this dashed line here, and a point here is not an image, is not in the image set of this mapping here. So hope this gives you a rough idea about the linear image of closed convex cones. And next, we are going to talk about the linear image of closed convex cones and its connection with the problem called the positive semi-definite completion problem. And I'm pretty sure you are all familiar with this problem, but let me just go through this quickly once more to get familiar with the setting here. So in the PSD completion problem, we are given an undirected graph G with n vertices. And additionally, we have a vector A whose length, which is a column vector, whose length is the number of edges in the graph G. And we're looking for a positive semi-definite matrix X so that the ijth entry in this PSD matrix X equals the ijth entry in the column vector A. So the column vector are indexed by the edges in the graph G. So for example, the question is, can we find values for the free entries in this question marks so that the matrix X remains becomes a still positive semi-definite? And in this case, the graph G looks as follows. We have the vertex 1 corresponds to the first row and column. We have a self loop because the diagonal entry has a value on it, which is 7. 1 and 2 is connected because there is an entry corresponds to the 1/2 entry in X. And if we can find such a completion, then we call the vector A PSD completable. Now, how is this problem related to the linear image of closed convex cone? Because the set of PSD completable vectors can be represented as follows. We define a projection P, which maps any PSD matrix into a column vector in Re by writing down the corresponding entries Xij in the corresponding position. And clearly, for any vector in this projected set is PSD completable, because that's how we constructed the set. If any PSD matrix here, its projection has to be PSD completable. So in this paper, they have answered the following interesting question, namely, when is the projected set is closed? And actually, they give a very characterization for this problem with a very nice combinatorial. They have a combinatorial characterization of this problem, namely, the projected set is closed if and only if L and L complement are disconnected, where L is a set of vertices in the given graph which has a self loop. So a self loop is an edge connecting the cell. So if we look at our example here, a self loop would be the vertices 1 has a self loop connecting to the self. The vertex 2 has a self loop connecting to self 3. Now the complement is 3 and 4, the remaining 2 vertices here. Now if you have followed the theorem, then you know that the projected set is actually not closed, because here L and L complements are actually not disconnected. They are connected because of this edge here. So this is a very nice result. Its proof is very elegant. It's very simple with elementary arguments. So I think it might be helpful to go through it quickly. As you may find it helpful for proving other results. So to prove this statement, we first go from the direction if L is disconnected from L complement, then the image of the PSD cone is closed. So as we mentioned already, to show that this set, image set is closed, we simply take a sequence in this set, which has a limit A, and all we need to do is that we have to show A is also in the set, namely A is also PSD completable. Since all the AI is PSD completable, there exists an auxiliary sequence big Xi, which is positive semi-definite, whose projection is little ai. Actually, we look at a special case here. If L is all the vertices, so namely all the diagonal entries are specified here, but that means the diagonal elements of all the matrices Xi in this sequence actually is converging to some constant. That's the diagonal entries here. So that means the diagonal elements of Xi are actually bounded. And it's an elementary exercise to show that if a positive semi-definite matrix has a bounded diagonal elements, then the whole matrix is bounded because off-diagonal elements cannot be too large or too small. So if you have a bounded sequence, then there exists a convergent subsequence, and we just assume that Xi itself is convergent to some X positive semi-definite. Now, by continuity of the projection, we have the projection of this limit X is precisely the little vector A at the beginning. And this shows that the vector A is PSD completable, which means it is in this set again. And this shows that the linear image is also closed. The general case is actually an application of this special case. In the general case, not all the diagonal elements are specified. So for example, in this case, only the first two elements are specified. First two diagonal elements are specified. So L is 1 and 2 only. We can simply apply our previous argument for the special case to the first 2x2 leading block here and conclude that there exists a PSD completion for the leading block here. And for the lower right block, there always exists a PSD completion. And to see that, we simply take any completion, not necessarily positive semi-definite. And then since the diagonal entries are not specified, we can simply add a big identity matrix to this lower right block. And this gives you a PSD completion. So this block is always PSD completable. Now, by our assumption, L and L complement are disconnected. So we have the freedom to choose whatever values we wish for those off-diagonal block. So in particular, we choose it to be 0 here. And such a completion is positive semi-definite, which shows that the set is closed in the general case. Now, to show the converse direction, actually we show that if L is not disconnected from L complements, then the set is actually not closed. We again start with a special case where we only have two vertices. So we're looking at the 2x2 matrices, which is pretty simple. For example, we construct a sequence of PSD completable matrices. So the matrix has K inverse in the first diagonal entry. One is off diagonal, and it remains to ask, can you find some values here so that this matrix is positive semi-definite? Well, the answer is yes. You can just take a big value for nabla, and that gives you a PSD completion, which is denoted by xk. Now, with this in mind, we can just construct a sequence AK, which is the projection of xk. Now, since xk is positive semi-definite, AK is clearly in the image set of the PSD positive semi-definite cone. And what is the limit of AK? And such a sequence AK converges to 0 and 1 because K inverse goes to 0 and 1 remains 1. But the limit A is a partial matrix 0, 1, 1 here, and this matrix is not PSD completable because if you have a 0 in the diagonal, and to be positive semi-definite, the corresponding row and the column has to be 0 as well. And that means we have constructed a sequence AK in the set, but it has a limit which is not in the set. And this shows that the set is actually not closed. Now, the general case is actually a special. It actually uses this special case by simply looking at the 2x2 submatrix generally associated to any vertex in L and J in the complement of L. Because if there is a 2x2 submatrix that cannot be completed, then the whole matrix is not PSD completable. So, all right, so that's the end of the proof. Are there any questions before I move to the next topic? Right, okay. If not, then I will proceed. So next, I will move to another interesting result from the paper, which is about the boundary structures of the linear image of a closed convex cone. And this result has some interesting connection with feature reduction and exposed phases. So I'll give a short introduction to feature reduction first. So what is feature reduction? Actually, the problem starts with strict feasibility, a constraint qualification for conic feasible set. If we are linear mapping A and see a closed convex cone, we can define the following set, which is intersection of an affine space and the cone. And this feasible set and many interesting problems can be modeled using this feasible set, including the PSD completion problem. And quite often, people find it very difficult to solve problems, optimization problems, or feasibility problems for general conic feasible set. So one way to make it easier is that we have to impose the so-called strict feasibility condition on this feasible set, which requires F to contain a feasible solution X in F, and X has to stay in the interior of this closed convex cone C. Now, without this condition, then many bad things can happen. For example, the KKT condition is no longer necessary for optimality. For solvers that relies on solving the KKT system, like interior point method, it might suffer some difficulties. Strong duality may not hold. So typically, you look at, especially for optimization problems, where you would like to have a reliable lower bound, for example. A standard strategy is to look at the dual problem and compute the dual objective function. That's what's but if strong duality does not hold, then your dual objective function does not reflect the true value, true optimal value. Small perturbations may render the problem infeasible because you don't have a point in the interior. And for all those reasons, many solvers might run into numerical errors. And actually, this is a very serious problem. There are examples of semi-definite programming with whose problem size is tiny. For example, X is just 5 by 5 PSD matrices, but it is so ill conditioned that even commercial solvers returns garbage for you. Now, fortunately, there is a way to to handle this problem, which is called feature reduction. And it is a regularization technique that can be used for any abstract convex programs without strict feasibility. So it covers definitely a lot of different problems. We will especially talk about the linear program and semi-definite program here. The idea of feature reduction is actually very simple. Let's use linear programs as an example. If we have a linear program whose feasible set is depicted as follows, you can see that because the variable z is fixed to be 0, the feasible set is actually not 4-dimensional, and therefore it's not strictly feasible. And feature reduction simply removes this redundant variable z and gives you a problem which is 4-dimensional. So in general, the variable, so of course, if you see a variable like this, z equals 0, then you should clearly remove it. But feature reduction actually handles something more general, because in general, you may not have a 0 variable that is stated explicitly in the problem formulation. It might be hidden. It might be implied by a set of linear equalities and inequalities. And it's a highly non-trivial task to find this. And this is actually the key of feature reduction. So let me elaborate this idea further using semi-definite programs, which is more relevant for the PSD completion problem. So if we have defined a spectral hadron in this way, let's look at what a feature reduction does. So let's start with a special case. Now, assume that all the feasible matrices X is actually block diagonal with a 0 diagonal block. Then the problem becomes simpler because we know that X is positive semi-definite if and only if this non-zero diagonal block R is positive semi-definite. And that means we can replace this PSD constraint by this smaller PSD constraint and just remove all those extra variables. And this uses a smaller problem, which is what feature reduction does in this special case. So this case is is essentially the same as the previous linear program example, where a variable is explicitly told to be 0. So you can remove it directly. Now, the general case is more complicated. Such a 0 diagonal block may be hidden from the user. If strictly feasibility fails, then there always exists an orthogonal matrix P, so that if you pick any feasible matrix X and you compute this orthogonal transformation, then you will end up with the same block diagonal structure with a 0 diagonal block. So essentially, this means that if strict feasibility fails, the orthogonal transformation is essentially a rotation of the feasible set F here. So after rotation, then you can see that all the feasible matrices has a block diagonal structure, and therefore you can proceed with the same argument in the special case here and end up with a smaller problem. And the whole story about the feature reduction is how do we find such this orthogonal transformation P here? And this problem is highly non-trivial. So let's see how we can find this orthogonal transformation intuitively. If strict feasibility fails, set is satisfied, then we know that there exists a matrix X satisfying this equality constraint, and X is positive definite. So interior of PSD is positive definite matrices. So you have X star laying in the intersection. And if strict feasibility fails, then there exists no matrix in the intersection. Now this set is an open set, so there exists no matrix in the intersection. But then we know that those two sets are convex sets. And therefore, we can call the hyperplane separation theorem, which states that there exists a separating hyperplane separating those two sets. And such a separating hyperplane can be used to construct this orthogonal transformation P that we are looking for easily. So they are in some sense, they are actually equivalent. And this separating hyperplane W in the context of Fisher reduction is called an exposing vector. And what is good about this, what is magic in the Fisher reduction is that such an exposing vector can always be found by solving an auxiliary system stated here. And then you find this separating hyperplane by setting W equals a adjoint V. So here is a description of the Fisher reduction algorithm. If we are given a feasible set F, now exactly one of the following statements holds. Either F is strictly feasible, then we're happy, we don't have to do anything, or F is not strictly feasible, and in that case, we can always find a vector V so that this auxiliary system holds. And as we just discussed, by solving this auxiliary system, we obtain exposing vector W, which was the separating hyperplane in the last slides. And this separating hyperplane gives you a rotation, which you can discard the extra zero redundant block to obtain a smaller problem. Now, once we get a smaller problem, if it is strictly feasible, then we are happy. And if not, we can actually repeat this procedure to this smaller problem until we obtain a strictly feasible formulation. All right, so why do we call this exposing vector, and why the whole algorithm is called Fisher reduction? That can be explained in the that is what we are going to do next, the connection between Fisher reduction and exposed phases. So, so exposed phases was also discussed in the previous talk. Let me just go through it slightly here again. If we have a convex set C, a phase is essentially a generalization of vertices. So if we pick any elements X in the phase, so that the element X lays in the line segment between two elements Y and Z in the set, then we must have that Y and Z is also in the phase. So for example, a vertex is a phase. So Y is a phase because by the definition of vertex, it cannot be written as a convex combination of any two different points in C. So this definition holds trivially. Each edge is a phase of dimension 1, because if you pick any 2 points in the convex set C, the line segment connecting those 2 points, if the line segment of connecting those 2 points has a non-empty intersection with this edge here, then you can see easily that those 2 points have to lay inside this edge. So this edge is also a phase. So the phase, the empty set and the convex set C itself are clearly a phase of C, and in that case it's not proper. So otherwise we call F the phase F proper. So the phase is definitely something about the boundary of the convex set. So the next question is, what is an exposed phase? For example, if you have a vertex, you can draw a hyperplane which intersects the convex set, gives you this vertex here. And in that case, if you can find such a supporting hyperplane, then this vertex is called exposed. For example, the edge here is also exposed because you can find such a hyperplane. But what is interesting is that not all the faces are exposed. An example is given here. This is a union of a unit disk and a square here. Now, the point A is a face. However, it is not exposed because the only supporting hyperplane intersecting A is this vertical line here. All right. And this vertical line actually contains the whole line segment connecting A and B. So it does not give you A. It gives you something extra, and therefore the face A is not exposed. So that's exposed face of convex sets. Let's look at a special case of exposed face for convex cones. So the definition is essentially specialized to convex cones. The convex cone is itself a convex set. And in that case, the supporting hyperplane boils down into a linear subspace, which is characterized by a vector V, by the orthogonal complement of a given vector V in the dual cone C star. And in that case, we say V exposes F. For example, in this example of linear program example, we know that the feasible set does not satisfy Slater's condition, and we can construct an exposing vector V, which is 0, 0, 1, which is clearly in the dual cone of R3 plus, and that vector exposes the minimum face of F, the minimum face F of the non-negative orthons containing the feasible region. Indeed, if you check the definition, the face F is everything of the feasible set intersecting what is orthogonal to V. But what is orthogonal to V is everything that has 0 in the last entry, because if you multiply V by a non-negative vector, which is 0, then the last entry has to be 0 here. And that eliminates the third dimension here. So, okay, so the connection between Fisher reduction and exposed faces. We have stated the theorem of Fisher reduction algorithm here again. And this auxiliary system solved by Fisher reduction algorithm essentially says that this vector W exposes a face F of the cone C containing the feasible set. And that explains the reason why we call the algorithm Fisher reduction, because we are actually looking for face of the underlying convex cone, and the vector W is called an exposing, and that's the reason why we call the matrix or vector W as an exposing vector here. And also that's the main idea of Fisher reduction, where you try to find a face, a smaller face of C, a proper face of F of C containing the feasible sets. And that's the reason why we can reduce the dimension of the problem. So, right, now, are there any questions so far before we move on to the second main result? Okay, so if not, let's proceed. So the second main result in this paper states as follows: if we could find a vector V so that the auxiliary system in the Fisher reduction algorithm is satisfied, which means from the previous slides that A star V exposes a proper face of C containing the feasible region F. And that is correct if and only if the vector V exposes a proper face of image set AC containing the right-hand side B. So this result establishes a connection between the boundary structure of the feasible set F and the boundary structure of the image set AC. So that's a very interesting result because the first characterization was used in the feature reduction algorithms, but it's sort of abstract and hard to understand on its own. And having this alternative characterization in terms of the linear image of C gives you a different way to view the same thing. And sometimes it can be helpful to understand the problem better using this alternative characterization. For example, let's look at the following concrete example. We define the linear mapping A from the 3x3 positive semi-definite matrices to R2, and the right-hand side B is a vector 1 and 0. Oh, sorry, the linear image is defined by mapping the first diagonal entry in X and the last diagonal entry in X. Now, clearly, just like the previous example, the image is all the non-negative authors in R2. So that's the image, and the right-hand side is a vector B, which is 1, 0, which is here, and the theorem says that if V, which is 0, 1, exposes a face of image set containing B, which is clearly the case here. If you draw the vector V, which is here, and the orthogonal complement of V, which is this red line here, and this red line clearly contains the face of the non-negative orthons containing the feasible set B, which can be visualized here. And by the theorem, we know that A star V, which is this 3x3 matrix here, will expose a face of the PSD cone containing the original feasible set. And clearly, it's not possible to visualize what is happening in the original problem. However, if you look at the image of the PSD set, then we can visualize it in this way. So, of course, both characterizations do not use a very efficient way to compute the actual exposing vector. It's mainly theoretical, gives you a different way to see how it works. But it does have another useful aspect, which is related to the so-called singularity degree here. So let's go back to the feature reduction algorithm. Again, we see that if F is strictly feasible, then we're happy. And if not, we can solve this auxiliary system to find a face containing the feasible region. But again, if this does not make F tilde a smaller problem, F tilde strictly feasible, we can repeat this algorithm over and over again. And it is natural to ask how many steps do you need before you end up with a strictly feasible formulation eventually. And such a question is already imposed in the literature. And John Soong was the first one who realized that the number of steps, which denoted by the singularity degree, is a very important parameter. And this parameter was studied recently by many experts in this area. And Stone was the first one who realized that the singularity degree provides an error bound for solving this error bound for computing the distance for computing an upper bound of the error of a given solution to this feasible set F. And this error bound was very useful, and later on, many new papers have come out relating the difficulty of solving the problems related to a feasible set F and the singularity degree. And also, 2 weeks ago, there was also a talk talking about the singularity degree and its relation with the solution size of the solution size of the feasible solutions in the feasible set F. So here is the second main result here. So it's actually it's actually identical to the one presented earlier, but here it is slightly stronger, where we put a minimal here. So minimal here, it means that this exposing vector gives you the smallest face of C containing F. So that means after reducing the problem size using this exposing vector, the dimension of the problem becomes the smallest possible, and the problem is strictly feasible. And in that case, the singularity degree is exactly 1, because you have found the strictly feasible formulation in one step. And this alternative characterization sometimes gives you information about the singularity degree where it is not easy to see using the standard characterization. For example, let's look at the following example, which gives for a given linear mapping A from the 3x3 PSD cone to it's R3 here. So again, it's similar. We have the first diagonal entry 1x11, the last diagonal entry x33, and additionally we have the last entry, which is the x22 plus x13. And we look at the right hand side, B is 1, 0, 0. Now you can figure out the linear image of a the linear image of PSD cone under A is everything non-negative in R3 union X and YZ, where the first entry and the second entry are non-negative, and additionally X times Y greater or equal than Z squared. So the feasible set looks as follows. So you have a non-negative oscillator here, and this is handled by the second part. Now, the vector B is here in the red dot here. And it is again clear from the picture that if you have to find a supporting hyperplane containing this vector B here, it will necessarily include the whole surface here. So that means the smallest face containing B is not exposed. And therefore the singularity degree is at least 2, because if it is exposed, then from the theorem in the previous slide, if we could find an exposing vector for the minimal face, then that means we find the minimal, that means for the original problem, we also find the minimal face, which would imply the singularity degree is exactly 1. And such an observation may not always be clear for the original set, but for the image set, you can still show it in this case. Yeah, I guess I'm running out of time. Let's look at the last part, an interesting application in the PSD completion problem. So in the PSD completion problem, we have an undirected graph G, as mentioned earlier. And this problem can be modeled as a PSD feasibility problem, where you are looking for PSD matrices where certain entries are fixed to be Aij. Now, an interesting observation is that each click in the graph G actually uses an exposing vector for F. So you can reduce the problem size of this. You can reduce the dimension of this set F here using those cliques or the exposing vectors. For example, if we have a PS completion problem here, this 2x2 submatrix is a clique in the underlying graph used to reduce the problem size of F. And in fact, if you look at this clique here, second clique here, and the third clique here, it eventually reduces the problem size from 4-dimensional to 2-dimensional. The last result from their paper, or the last result that I presented from their paper, is that if the subgraph G associated to the vertices with self loop, that's vertices with that's the matrix with diagonal entries specified, is actually chordal. So those are graphs with no triangles in it. Then the exposing vectors obtained in this way from the cliques are actually forming the minimal phase containing the feasible set. So that's an interesting result. And this also answered an empirical observation in the literature where applying this technique, we have reduced the problem size substantially. As you can imagine that when the problem size is reduced sufficiently to a sufficiently small problem, and then those linear equalities imposed on those variables actually means you only have to solve a linear system instead of solving a semi-definite program. And such an empirical observation is partially answered by this theorem here. There was another paper by Nathan and Professor Wolkowicz, which used this technique to solve huge PSD completion problems using the Fisher reduction in this way. So, right, I think I've finished. Thank you for your attention.
Hey, thanks, Hao.
Yeah, thank you.
Well, any questions? Discussion? We have some time.
Yeah, I have a question.
Yeah.
Can you go back to your picture of the showing the singularity is x2? Yeah, this picture. So yeah, this picture. So is this a singularity degree exactly 2? I mean, you can see this B is not exposed, but then if you reduce it to this plane, then you apply. You find another single exposing vector, then you will be able to expose B, right?
Yeah, exactly. Your observation is absolutely correct. So the singularity degree is exactly 2.
So yeah, then I think so. The singularity degree of the linear image is exactly the singularity degree of the original problem, right? It's not just 2.
Let me see. So the singularity degree of the image set is the same as the singularity degree of the original set. Yeah, I think you are right. If we look at this, actually this theorem.
Yeah, because because the linear image may not be exposed, so the definition of this singularity should be a little bit different. I mean, there's no auxiliary problem, but you only think about if this face is the minimum face is not exposed, then you find the exposing vector and expose the face containing this minimal face, and then you treat this face as a cone. And if the minimal face is still not exposed in this bigger face, then you do it again, until the minimal face becomes facially exposed in the bigger face. So that's the definition of the singularity degree of the linear image. So there's
Right. Yeah, that's a good question actually, because in the standard setting where we usually work with closed convex con C, where all the faces are exposed, but the linear image may not be exposed.
Yeah, if everything in the image is exposed, then the singularity is just one. There's nothing there's nothing interesting, right?
Let me see. So you mean if the linear image,
if this is facially exposed, then everything is every face can be exposed. So there's a therefore it's not true. So it must be not facially exposed.
Right.
Somehow.
Right. You're right. If this is exposed, then there always exists a V so that this holds, and which gives you an exposing vector for the minimal phase for the original problem. Yeah. So for example, if this phase, the smallest phase containing this point, is this phase, this horizontal line here, right?
Yeah.
And this phase is not exposed, but if it is exposed, then we find the singularity degree of the original problem 1 exact. Yeah, you're right. Yeah, it's the thing is the structure of the linear image is also very complicated. So in general, it's pretty non-trivial to check if.
This is my conjecture. I don't know. But this was if this is paper only the singularity degree 1 is discussed.
So there's a problem, or maybe a connected result about the image being polyhedral. Because if the image is polyhedral, then the singularity degree is at most 1.
Yeah. Yeah.
But then
so
yeah, so does that come into play at all?
Yeah, I think so.
With this discussion?
Yeah, so yeah, this is related to what Fei asked. So Fei was claiming that if the smallest phase of the image set containing B is exposed, then the singularity degree of the original problem is 1. Because if it was exposed, if the smallest phase of AC containing B is exposed, then we have a vector V exposing the minimal phase. And by theorem, A star V is going to be a minimal phase of the original problem containing the original physical set. So the singularity degree is 1. So in general, there are 2 scenarios. One is what you mentioned, if the image set is a polyhedron. And in that case, all the phases are exposed. And therefore, the singularity degree is always 1, at most 1. Now, their second case is that not all the phases of the image set containing B are exposed. And then,
I mean, the minimal phase is not exposed.
Yeah. That's what what has to be. If the for we can in this case, yeah, the minimal phase is not exposed, then the singularity degree is not 1. But I think if B is here, then this phase is exposed, then the singularity degree would be 1. Oh, it would be 0, 1 or 0. Yeah. So actually, it depends on both the linear image and the B. It depends on where B is. So that's what you said. It depends on the minimal phase containing B. It's not a about a particular phase. What is relevant is the phase containing the minimum phase containing B. So I think like as we discussed earlier, like this algorithm, like in general, this algorithm would just solve a random instance completely by the problem collapses into solving a linear system. So I think it's still not clear in the literature about when does this happen. So here, in case the graph is caudal, we have the minimal phase here. But it can be an interesting question to ask if when does this algorithm actually finds the PSD completion by solving a linear system? So when does the clicks can be used to decompose the problem, to collapse the problem into solving a linear system? The problem could be related to the graph rigidity, or should certainly be related to the graph structure, rigidity, etc.
Yeah, you can carry out this theorem to the EDM completion problem, right? Instead of a PSD cone. Maybe you have a same theorem for the EDM cone.
Right. Yeah.
Then you can see the stress matrix of the caudal graph. It's like it's exactly n minus 1 minus r.
Mm-hmm.
No, it's exactly like maximum. So the stress matrix is like so the EDM completion problem is so you have a EDM, and then there's a projective entries, and then the max rank. Suppose the max rank of the EDM, the maximum dimension of the EDM is R. Then your stress matrix will be n minus r minus 1 for caudal graphs. Well, no, and a caudal graph is you can always complete it to maximum degree, right? Yeah, mm-hmm. Forget about that.
What do you mean? Caudal graph is always what?
You can always complete it, but it's nothing to do with the degree.
Yeah.
Cannot be okay. It may not be completed to full rank, right? Can caudal graph always be completed to full rank, to maximum dimension, like for EDM completion problem?
Well, depends on so like for positive definite completion, you have to start with that all the principal minors are positive definite. So if you're starting with, and it depends what embedding dimension you start with. If you don't have the right embedding dimension, then you can't complete to a high embedding dimension because you're stuck before you start. Same with the positive definite completion. If you have a principal minor that's not full rank, then you cannot complete the matrix to full rank.
Mm-hmm.
So if you're trying to do a PSD completion and you have a submatrix, principal submatrix, which is not full rank, then you're stuck. You can never complete to positive definite.